Hello, and welcome back to the MCAT grind. We have Organic Chem Chapter 3, Bonding. Now, bonding is a short chapter, but please keep in mind that there are always small discrete questions that will come up because chemistry, organic chemistry specifically, is a huge component in the biological section. So you may see discrete question forms or standalone along with the passage questions. Now, we have principal quantum number, azimuthal quantum number, magnetic quantum number, and spin number. These have been described in earlier chapters, primarily about the electron shell orbitals. Now, just to review, N is a principal and it describes the energy level of the shell. We have seen that hydrogen only has one single shell, so there's only N of 1. However, lithium has 2 shells, right? The first shell containing the 2 electrons plus an additional shell containing 1 electron. Now, we have azimuthal quantum number, which describes a subshell. Within that shell, there are subshells within it where electrons can reside in. Now, to describe them, there are s orbital, p orbital, d orbital, and f orbital as the common ones. It goes from 0 to n minus 1. N is the principal quantum number. Magnetic describes the orbital. Imagine that all planets are orbiting the sun, but they follow the exact same path. Now, electrons don't do that. They each, even in the same subshell, they can follow a different path, maybe slightly off-angled from another, and that describes a magnetic number from -1 to +1. If is an s orbital, it is a sphere. P is a dumbbell shape. Now, what does this mean? -1 to 0, negative L to positive L. So if I have a principal quantum number of 2, my azimuthal can go from 0, 1 to 2, and my orbital within that could be negative L, or -0 is just 0, or from -1 to 0 to 1, or -2 to 0 to -1 to 0 to +1 to 2 for each of the azimuthal subshells respectively. You will notice that S having azimuthal number of 0 would just denote a sphere because there's nowhere to go for the magnetic orbital, right? If it's 0, negative L of 0 is just 0, so it's just going to end up in the same little ball region. That's where the electron density will be. Now, if it is 1, the azimuthal number is 1, you can see that it goes from negative L, -1 to 0 to +1, where there will be 2 electron densities, where there's a positive region, 0, no electron density, and a negative L region. So hopefully that makes sense. And as you go up, you will have different electron densities found in different regions. And finally, we have the spin. The spin quantum number describes whether it's positive or negative spin. It spins in one direction or the other direction. Next, we talk about the bonds. We have sigma bond and pi bond. Sigma bond is denoted like this, and pi bond is the pi we're familiar with. In a sigma bond, there are 2 electrons participating in it, like how we see single bonds. So a single bond is just 2 electrons sharing and forming that bond together. Now, we have pi bond also, and pi bond acts a little differently. It is the two electron orbitals, right, found in a dumbbell shape that are connecting with each other. They're sharing the electron cloud overlapping together, right? So it is both of the dumbbells forming together that makes one pi bond, which trips many up because there are 2 clouds coming together to make one pi bond. And if you want to add another pi bond, remember the atoms are in 3D shape, so we have sharing of electron clouds along these 2 pair and these 2 parallel pairs. Hopefully that makes sense. So those denote the single bond with 1 sigma bond, and double bond with 1 sigma and 1 pi bond triple bond contains 1 sigma and 2 pi bonds. As you increase the number of bonds, it becomes shorter, inflexible, but also stronger because they're much closer and sharing of the electrons. Next, we have the hybridization. In sp3 hybridization, we have one s orbital, which is 0 in a 0 subshell, mixed with 3 in the p orbital. What we get is electrons, instead of staying discretely in their own orbitals, they jump around and share and hybridize into sp3 orbitals. So 1, 2, 3, 4 of them, and they are shared into 4 orbitals of equal energy levels. Now what we call this new hybridized orbital has 25% of s character and 75% of p character, because what we put in an ingredient basically is 1s and 3 pi, and that gives us 25% of s should be in here, and 75% of what's in here should be p. Now we have sp2 hybridization, which is 1s and 2p, giving us sp2, and you will notice that it is much closer to s orbital because it has a greater contribution of s and less contribution of p. 33% from s and 67% from p. Finally, we have sp bond, which consists of 1s, 1p, and that just makes an sp orbital, which is right in between the two orbitals. And it will be much closer to s than the original sp3 character because it shares 50% s and 50% of pi bond. Alright, so what does this tell us? Well, sp3 hybridization is typically for single bonds, sp2 typically for double bonds, sp typically for triple bonds. You will see that there are unhybridized orbitals in here. So in sp2, there is one unhybridized p orbital, and sp, there are 2 unhybridized p orbitals. And those, because of they're not hybridized, they can participate in these sharing of bondings and participate in a pi bond. That's why in sp hybridized orbital, we have 2 pi bonds going on. Right? The 2 p orbitals are able to participate in that pi bonding. Alright, then finally we have resonance. Resonance describes how electrons don't tend to stay in one atom, and when you have a bond occurring, they could jump to the next, and there continuous flow of a general electron cloud. Just as you can denote the Lewis structure here, I have not dotted the electrons for visualization. Here we should fill up the max set of the electrons. Here should be 1, 2, 3, 4, 5, 6. So we know the native state of oxygen has 6, so and it wants 8 perfectly. No, it has 8. So 8 minus 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so this oxygen will be negative in state because it's not part of its native. I think 7, right? Oxygen has 7. 1, 2, 3, 4, 5, 6, 7. So oxygen here will be positive, and this will be negative because it only has 1 bond, whereas it has 3 pairs of electrons here. So 1, 2, 3, 4, 5, 6, 7. Okay, next we can see that the hybridization, or not hybridization, the resonance between these two, because it can exist in both of these resonance forms, that we can simply denote it like so. And there's sharing of the extra electron charge, because it's not stable in just one spot, but rather moves around about. You can also see this in much bigger forms of typically sulfur and nitrogen. Those are common atoms that will participate in resonance. Another instance is in cyclic structures. You may see these double bonds that jump from here to here and bumping this into another. You can see this would jump up and knock this up here, and this electron will go up here into this resonance structure. Alright, because of this extra resonance, it builds stability and helps makes the resulting structure stronger. Alright, so that's about it. Take care.